Hello, this is the third video of this series of videos on graphing techniques, and we have already computed a bunch of information regarding this function fx equals to a to the x sine x, and things that we have computed up to now are first derivative, second derivative, the critical points where the first derivative is 0 or undefined, the second degree critical points where the second derivative is 0 or undefined, and then we have plotted the critical points of first derivative in this number line, and we have also plotted the critical points of the second derivative in its respective number line. We are using a template which is useful for problems like these, and this template can be downloaded from the description of the YouTube video or from our website cheenta.com. We will proceed to discuss maxima, minima, and inflection point. Now here is a word of caution. This particular video is not about the conceptual background of maxima, minima, or inflection points. So there will be very few conceptual remarks. That is, there will be very few answers to questions why it works. For example, we will define inflection points as points where the critical points, second degree critical points, about which the sign of the second derivative changes. Now you might be interested in a little bit more motivation and explanation of why it is so. However, that discussion is out of the scope of this video. We are only interested in solving the problem. The conceptual remarks are for another video and classroom lectures. So let's come back to this one. We will talk about maxima, minima, and the points where the curve basically reaches a peak or a trough. So we want to focus on these critical points of the first derivative that we have already found. And we want to see how the first derivative changes, how the sign of the first derivative changes about these critical points. At the critical points, the first derivative is of course 0. To find out what's happening in between two critical points, what we can do is we can pick a value from that interval. Let's say we are interested in the interval negative pi by 4 to positive 3 pi by 4. So we can pick any value in that interval, let's say 0. And we can plug that in, that value in to the first derivative. If that is positive, then the first derivative is positive in this entire interval. How do I know that? Well, it actually follows from intermediate value property theorem, but again, as I said, this is not the place for the conceptual remarks, so that is for a different video. For this one, we use just this technique. We pick a value from negative pi by 4 to 3 pi by 4, or from each of the intervals we are interested in. We plug that value into the first derivative. Whatever the sign of the number we get, that is the sign of the first derivative in that particular interval. So for example, let me compute this for x equals to 0. For x equals to 0, we have square root of e to the power 0 times sine of pi by 4. And this is clearly greater than 0. So we know immediately that in this interval, in the interval negative pi by 4 to 3 pi by 4, this first derivative is positive. Now you can check by picking up values from each of these intervals. For example, from 3 pi by 4 to 7 pi by 4, you can pick a value between these two numbers, plug it into the first derivative, and find the sign of the first derivative in that interval. You will see that this one will be negative. It will alternate actually. The next one will be positive. This is negative and this is positive. So really it's alternating in this particular case, but it is not necessary that it will always alternate for other problems. So you have to be a little careful and you have to pick up values and check for each of the intervals. We do the same thing for the second derivative. So again we have 5 different intervals. Let me pick the middle one. Let's say I want to know what is the sign of the second derivative between negative pi by 2 to positive pi by 2. So what I do is I'll pick a value from this interval, let's say 0, and I'll plug it in the expression for the second derivative which we have found earlier. So this is 2 times e to the power 0 cosine of 0, which is just 1. And we are only interested in the sign of the number. So this is greater than 0. We really don't have to compute the final value. In fact, in most cases, you will not compute the final value. You will just look for the sign of the final value. So in this case, obviously, this is positive. So let me mark it positive. So this is positive. Now, if you compute the other values, you will also see that this sign also alternates. Okay, so we have found a very interesting description of the first derivative and the second derivative. We have found where let me make some space. We have found where it is positive, we have found where it is negative. Now, when the first derivative changes from positive to negative, when the first derivative changes from positive to negative, like the one that happens here, about negative 5 by 4, we will have a maxima, local maxima. So let me denote it like this. And you can see why. Because before it is increasing, before negative pi by 4 it is increasing, so the first derivative is positive. After negative pi by 4 it is decreasing, so the first derivative is negative. So it makes sense why it is a local maxima. Similarly, here it will be a local minima from negative to positive, a local maxima and a local minima. So we have the maximas and the minimas right here. Maxima is at negative 5 pi by 4, comma, we have to also find the y coordinate, so this is the x coordinate. So we have to find the y coordinate, we plug in this value into the original function to find the y coordinate. So we plug in the value in the original function. So we have e to the power negative 5 pi by 4 sine of negative 5 pi by 4. So that is one of the maximas, obviously. The other maxima is at 3 pi by 4. So 3 pi by 4 comma e to the power 3 pi by 4 sine of 3 pi by 4. Similarly, you can record the minima here. We are out of space, but you can record the minima here. And minima would be at negative pi by 4, and obviously the other one is 7 pi by 4. So negative pi by 4 and 7 pi by 4. And we have to find the corresponding y values. So as I said, this is a lot of careful work and a lot of cataloging of the work that you do. We will find the inflection points in a similar way. Inflection points are points wherever there is a change in sign of the second derivative about the second degree critical point. So about each of these second degree critical points, we have a change of sign of the second derivative. It changes from plus to minus, minus to plus, and so on. So each of these, so negative 3 pi by 4, 3 pi by 2, and we have to find the y coordinate, of course, negative pi by 2, positive pi by 2, and positive 3 pi by 2. All of these are inflection points. So we have 4 inflection points, we have 2 relative maximas, we have 2 relative minimas. We've come a long way in describing the function, and in the next one, hopefully, next video, we will hopefully finish this off.